Okay, so here's what we were talking about last time. Talking about the fundamental theorem of line integrals. Again, the point of view that I want to take here, and I think this is a very valuable point of view, is to view this theorem and the next theorems that we're going to talk about as being just kind of analogs, arguably extensions, dimensional variations of fundamental theorem of calculus. It's really just like the fundamental theorem of calculus. And so we took a particular point of view on the fundamental theorem of calculus last time, and that is that the fundamental theorem of calculus that relates an integral to, this little formula f of b minus f of a that we're all familiar with. I want to interpret that as change, f of b minus f of a. So how much did this function f change? And viewing that as, in an integral, the accumulation of little changes. Right? So I think that's a great way to think about it, to start with change. In some sense, go backwards. Start with change. Start with the result, in the way we normally think about it, and show that that result, in fact, is an accumulation, namely an integral, over the interior. Okay, so we did the same kind of thing with the fundamental theorem of line integrals here. We made the observation that the boundary of a curve consisting of a starting point and an ending point, appropriately oriented, actually is an accumulation itself. Again, it's the sum of the boundaries over the little pieces. And that was this argument that we made about thinking about orientations. So again, if you have your curve here, it has a starting point and an ending point. Well, that is the sum of, and again I'm going to offset for artistic convenience, that little piece of curve's boundary, which has a starting point and an ending point, and then plus the next little piece of curve's boundary, which has a starting point and an ending point. You add those little pieces of curve's boundaries up. Note that all of the interior endpoints, little interior boundary points, appear twice with opposite orientations, and therefore they cancel. So, in some sense, all that stuff in the interior goes away because of the way we set up orientations. Critical to this is the fact that we set up orientations of boundaries in that very special way, namely positive on one side, negative on the other side, so that they would cancel. Okay. So, punchline then. This shows up in the algebra as this change that we're interested in is, in fact, an accumulation of little changes over the interior pieces, which you can write like this, which you could rewrite like that. This expression makes a reference to something that we know how to compute from Chapter 4. The change in the output of a function over a little short piece is computed with a dot product with the gradient vector. The old Chapter 4 fact. There's a relationship between input changes and output changes, and it's the derivative of the function. And lo and behold, we have a Riemann sum that is the very definition of a vector line integral. And so, sure enough, change accumulates. It accumulates in this particular way, namely as a vector line integral of a particular vector field, that vector field being the gradient of the original function whose change we're interested in. Okay, so there's the way we're going to write that as a theorem. We did an example last time. One last thing, let me say. The way this shows up, if we sort of fill this in on our diagrams that we've been developing, the idea is that if you have a curve and you look at its boundary, we've now found a complementary sort of operation. Namely, if you have a function, you can compute its gradient field. And the neat result is that this kind of evaluation of your original function over the boundary of that curve, namely that expression, equals this sort of an evaluation of that gradient field over the original curve, namely that expression. So again, the gradient is sort of complementary to the boundary operator in making two evaluations that equal. Okay, right. So we did this example last time. Let me not do it again, but I'm going to show you another example. I guess I'll first observe. Now it looks like the same theorem. It's kind of the same theorem. It doesn't look practically identical. The only difference here is that here I'm just allowing this curve to be in R3. If you think of it, if you look back at the arguments that we made in making this R2 conclusion, drawing this conclusion, which we again state in R2, we drew this picture. That was a two-dimensional picture. Made the argument, etc. Extending this to an argument in R3, just looks like that. Now it's an argument in R3. All the algebra is exactly the same. Nothing changes. Right. So theorem works in R3 as well. And it appears on the R3 diagram very similarly. All right, so I'm going to show you an example of doing a three-dimensional version of this. So again, suppose I want to compute a line integral. And suppose I'm given this vector field. This is the vector field I want to compute a line integral of. And I want to compute that line integral over that curve parameterized by, well, it's got this function here, and t starts at 0, ends at 1. And let's compute that line integral. Now, if you see this question on an exam, your temptation, at least at this point in the course, is going to be to say, oh, okay, well, I have the vector field as a function of x, y, and z. X, y, and z are functions of t. I can plug this into the parameterization formula for computing vector line integrals and take a deep breath and start chugging forward. And you can do that, I suppose. Let's speculate on what that experience is going to be like, though. Look at this formula for x as a function of t. It's got a lot of ugly in it. There's an exponential with a quadratic in the exponent. There's trig. There's a fifth power. There's a lot of bad in there. Right now, you could do that, and weirdly, it would actually work out, sort of unexpectedly. But it's a lot of stuff to write down. Right? It's a lot of opportunities for oopses, if nothing else. So let's make a different argument here. And the different argument is going to be to look at this vector field and observe that this vector field, in this case, lucky break, is a gradient. That vector field is a gradient of a particular function, and I can write that function down. There it is. We'll talk about where I got this function from in a couple seconds. For the moment, let's just celebrate the fact that, wow, we found a function whose gradient is the vector field in question. So this question could be rephrased as, instead of compute a line integral of a vector field, we could rephrase this as compute the line integral of the following gradient field. And realizing that we're computing a line integral of a gradient, not just a line integral of a just random vector field off the street, we're going to invoke this very powerful theorem for computing line integrals, vector line integrals of gradients. And what this says is I just have to take this little f function and plug in the endpoints and subtract, and poof, done. So that's what we do here. Right? We take this function f that we have found, plug in the starting and ending points. So plug in t equals 0, t equals 1. That gives me starting and ending points, which happen to be these 2 points. Plug into f, subtract, and there's your answer, 1. Didn't even really have to do an integral. It's a really nice result. Does everybody see how this works?
How do you get starting and ending points?
Right, so I'm given here that t starts at 0 and ends at 1. So you take those t values and you plug them into here, and that tells you where x starts and ends. Yep. Okay, so now I did sweep an important issue under the rug here. Let me confess on this and focus on where did I get this function from? I seemingly pulled it out of thin air. Now, in this case, you can look at this vector field and maybe sort of speculate on how you could kind of see it coming, what this function is. But in general, how would you find the anti-gradient? It's a nice little method. It's not that big a deal. I do have to start off with some bad news, and that is we're going to have to accept disappointment sometimes. Sometimes we're not going to be able to find an anti-gradient. And it's not because it's algebraically too hard sometimes, although I suppose that's true as well. But sometimes the reason we're not going to be able to find an anti-gradient is because it doesn't exist. This is a new kind of a problem. This is not a problem in single variable calculus, really. If you have a continuous function, it has an anti-gradient. It might be hard to write down. I might not personally be algebraically proficient enough to find that anti-gradient, but there is an anti-gradient. Excuse me, an antiderivative. When you're doing single variable calculus, there's an antiderivative. With anti-gradients, sometimes no. Sometimes there just isn't one. Okay. But if there is, here's how you would find it. If you want to find the function little f, whose gradient is the given vector field big F, well, the gradient is computed by that formula. The vector field whose anti-gradient we want to find, we know the components P, Q, and R. And so what I need to do then is one at a time, I need to look at these three equations, which I've written here, just to make them a little easier to see. And in each one of these, I'm hoping to find what this little function little f is. Now, weirdly, it does have to be the same little f in all three equations. And so that's the challenge. That's in some sense the problem, is can I find a single function little f that satisfies all three of these equations? And, well, if I can, here's how I would do it. I can take an x anti-partial of both sides here. Y anti-partial, z anti-partial. And what I get is that I need to compute these three anti-partials, and I need them to all equal to the same function. I'm going to put a little asterisk on that statement for the moment. But we'll get to the asterisk in a second. But if the same function f is going to satisfy all these partial derivative equations, then the anti-partials of p, q, and r with respect to x, y, and z respectively, well, they all have to be the same function. All right, now let's talk about the asterisk. When I say that f has to be, the anti-partial, the x anti-partial of p, the idea there is if I take this equation down here, the x partial of f turns into that. The x partial of the x anti-partial of p is that. But I have to acknowledge the possibility that I am allowed to have something here. I'm allowed to have an extra term as long as when I take the x partial of it, it gives me 0. And this is kind of like the integration constant when you're doing single variable calculus, right? I mean, whenever you take an antiderivative, you get to say plus c, because any constant you add in there, when you take the derivative, would give you 0, and therefore it's perfectly fine. The only difference here is that this, what I'm going to air quote constant, doesn't have to actually be constant. It just has to be something that when I take the x partial gives you 0. That means that this could be a function of y and z. It could be all kinds of weird and non-constant in terms of y and z, because that is still something whose x partial is 0. So the asterisk is, it's not quite fair to say that these three functions that you'll write down as anti-partials all have to be equal. They just have to be such that you can add a function of y and z to that one, a function of x and z to that one, and a function of x and y to that one, such that these things are all equal. All right, so let me show you what this looks like in practice. Here is a vector field. Here's an anti-gradient I want to compute, and let's play the game. So per up here, I'm going to compute the x antipartial of that first component, P. I'm going to compute the y antipartial of the second component, the z antipartial of that third component. So I'm going to do that. And let's see how it works out. These are the three equations that I get. Zoom in, focus on this. So first let me note these three antipartials that I first wrote down are not all equal. So don't make the mistake of thinking that this is a loser, right? That, oh, well, we can't whittle it. These three functions are not the same. Well, that's not the requirement, right? What's required is that we have to ask the question, can I sort of adjust with three functions over here to make these equal? And yeah, you really can. Here's the idea. There's an x squared y in these two. There's no sort of x squared y in there, but x squared y could be that function. The only requirement on C3 is that it not have any z's in it. So I could let C3 be x squared y, and now there's x squared y in all three equations. Ditto for xz cubed. There's no xz cubed in here, but it could be xz cubed there. And that's fine. And then finally, 2yz, 2yz. Well, there's no 2yz over here, but 2yz would be perfectly happy there. So with those choices, we found a single function that's equal to all three of these expressions. So it is x squared y plus xz cubed plus 2yz. And that's what f is. That's our anti-gradient. And check it. I think it's a worthwhile exercise to take this function, take its three different partials, take its x partial, its y partial, its z partial, in other words, compute its gradient and confirm that its gradient, sure enough, is that vector field that we started with. All right, is everybody happy with this little method? Okay, so that's all I'm going to say for now about the fundamental theorem of line integrals. We will say actually quite a bit more about it later on. There's a lot of related cool facts about the fundamental theorem of line integrals, gradients, stuff like this. I want to move on to some other theorems, though, for the moment, for the purposes of emphasizing the analogy and the relationship. So we'll come back to the fundamental theorem of line integrals later on and finish off all the other good stuff. So for the moment now, I want to go on to Green's theorem. Green's theorem is kind of a two-dimensional version of the previous theorems that we've talked about. Now, let me remind you what we've done so far. We revisited the fundamental theorem of calculus. Change accumulates over the interior of an interval. Then we've now done two sort of extensions of that. We did a kind of a two-dimensional version in the sense that we talked about a curve moving through a two-dimensional space. And again, over a curve, you can talk about at the endpoints, how much has a function changed over the course of that curve, and we viewed that as an accumulation over the curve. That ended up giving us the fundamental theorem of line integrals. Then we observed that there's a three-dimensional version of that as well. Again, still, change accumulates over a curve. It's morally the same. This is going to be different in a more fundamental way. Now, instead of talking about a path in whatever world it might happen to live, and looking at the boundary as being 2 points over which we compute change, now we're going to talk about a two-dimensional region, not a path. forever to shade these things in. The boundary of which, it's not 2 points, the boundary of this is a curve. Side note, an oriented curve. So what are we going to be interested in here? Are we going to be trying to relate a one-dimensional integral to a change, f of something minus f of something? No, the dimensions don't fit with that at all, right? So we're going to need to compute a different thing. What is analogous is we're going to be doing a computation. We're going to be starting off by considering an object that's computed on the boundary. It's just that now the boundary isn't 2 points. Now the boundary is an entire curve. What do we compute on curves? On curves, we compute vector line integrals. So specifically then, we're going to take our solid region, we're going to look at its boundary curve, and for a given function, a given vector field on that boundary curve, we're going to compute the vector line integral. And our hope is that there will be some complementary operation on the other side, giving me, hopefully, fingers crossed, some function such that over my original two-dimensional region I can compute a double integral that will give me the same value. So this would be analogous, again, if we're successful, fingers crossed, hope this works out. If we're successful, this would give me a theorem that's really very analogous to the fundamental theorem of line integrals, to the fundamental theorem of calculus, but dimensionally shifted, right? Instead of a one-dimensional curve with a zero-dimensional boundary, now we're going to be talking about a two-dimensional region with a one-dimensional boundary. So in a more significant way, extending the fundamental theorem of calculus. Okay, now I'm going to go ahead and get started on this. I'm going to be, again, ripping off, kind of cheating off of the work that we've already done in these other contexts. And the first thing that we did in those other contexts is we asked the question, do these boundaries kind of accumulate? Let me go back here to that picture. We asked the question, is it true that the boundary of that plus the boundary of that plus the boundary of that, etc., is the sum of those individual boundaries equal to the boundary of the whole thing? And we thought about the various endpoints and the orientations, the greens and the reds, and sure enough, all the interior stuff canceled, and it worked out. So, analogous question here. If I look at these individual little pieces here, let me zoom in so I can see this better. There we go. If I look at one of these individual pieces, if I think about what its boundary looks like, well, its boundary consists of these little pieces of curve. If I look at the boundary of each individual piece, if I add those up over the entire solid, is it true that the sum of those boundaries is equal to the boundary of the whole thing? And what we're going to find, amazingly, is that, yeah, it actually works. Because, again, just like with the curve, everything in the middle cancels. And here's what that picture looks like. So here are two pieces. Let's look at this piece first. That little piece of our two-dimensional region. It has boundary. Its boundary looks like that. Okay. Now let's look at this piece. Its boundary, again, playing by the usual rules, always go counterclockwise. Well, always go such that the region's on the left. Its boundary looks like that. So the sum of these two boundaries, some of those two boundaries is, well, I have 8 little pieces of curve. Let's draw our attention, though, to this edge That edge appears twice in this summation. It appears as part of the boundary of D1, oriented up. It appears as part of the boundary of D2, oriented down. That means that as part of computing the sum of these two, if I were computing these line integrals around these two boundaries, I'd be computing a line integral over this curve going up. I'd then subsequently computing a line integral of the exact same curve going the opposite way. I would get exactly opposing values. And they cancel. So interior pieces cancel. And you can see a sort of a generalization of this in this picture. We have this great big region. I'm focusing in on one little small part of it. And the summation of the boundaries of the various pieces, you can see I have them drawn on here. That edge is downward oriented as part of the boundary of that piece. It's upward oriented as part of the boundary of that piece. And so this edge cancels. Likewise, that edge cancels. All of these interior pieces, poof, disappear. Now, where are the pieces of boundary that don't cancel? Lots and lots of cancellation. That makes a huge mess. Lots of cancellation. I'll do it like this. What about that? Now, that is part of the boundary of that little sort of corner, little triangular, little odd-shaped little piece. But it's not part of the boundary of anything else. There's no. It's because it's on the outside of my original two-dimensional region. It's not. There is no other side over there to create an opposing oriented version of that. So that doesn't cancel. That stays there. And likewise, that piece doesn't cancel, and that piece doesn't cancel, and that piece doesn't cancel. The only things that don't cancel then are the pieces that are part of the boundary of the whole thing. So, wonderfully, boundaries accumulate. Let's see, where did I write this down? Yeah. So, the boundary of the whole thing is exactly what you get when you add up all of the little pieces you broke it up into, the boundaries of all of those individual little pieces. So boundaries accumulate. So this allows, by the way, I wrote this down algebraically here in this example. So in particular, note that each one of these edges I gave a name. Each one of these edges I assigned an arbitrary orientation just to be able to talk about it. So let's think about, in this piece, for example, going counterclockwise around the boundary of D2. Let's think through what is the boundary of D2 with these names, with those specific orientations. Well, boundary of D2, C4, going in the direction that I've assigned for C4, plus C5, plus C6, but it's not C7. C7 is defined as going up. Part of the boundary of D2 is the downward version of that. So that's a backwards of C7. That's minus C7. Whoops. So boundary of D2 is that. A similar argument you can argue what the boundary of D1 is. You can take these, you can add them up. Note the cancellation. C7 appears twice with opposite signs. And you see how the boundaries accumulate. This is just an algebraic sort of equivalent of what we argued here about that appearing twice with opposite orientations and canceling. I like the geometric version better. It's more satisfying. Okay, that having been observed, keep in mind what we're computing here. We have a two-dimensional region whose boundary I'm interested in. We have a vector field. We're trying to figure out what we're going to do with that. Don't really know yet. But in particular, it's circulation, boundary circulation of that vector field that I'm interested in on the left. And what I have just shown is that that is an accumulation over the interior. Now, let me extend the analogy. When we were talking about the fundamental theorem of calculus, we weren't interested in these boundary circulations. The fundamental theorem of calculus, we were talking about change. And we argued that change accumulated over the interior of the curve. Here, it's just a different boundary evaluation that we're interested in. Here, it's not change. Here, it's boundary circulation that accumulates over the interior. Not the interior of a curve, it's the interior of a region. Dimensionally different, otherwise structurally very analogous. Okay. All right, so I have an accumulation. This is always equal to that, no matter how I slice it. So if I take a limit, it doesn't make any difference. Something that's true is true in the limit. This is starting to look kind of like a double integral at this point. Note it's a summation over all of the pieces of a two-dimensional region. That smacks of double integral. Double integrals, though, have to have an area over here, which I don't. So you'll notice I both multiply and divide. That's perfectly legal. They just cancel right off. I didn't really do anything there. But now, structurally, this is a Riemann sum. There's a limit of a sum of some expression times area. So that's a double integral. The big question then simply becomes, in the limit, what happens to that expression there? So what is that limit? Now, there's some bad news here. We're trying to rip off what we did with the fundamental theorem of calculus and fundamental theorem of line integrals. In both of those instances, when we got to this point, it was a familiar expression. When it was change instead of circulation, this was what change per unit length was the derivative. In the fundamental theorem of line integrals version of this argument, this was just the gradient vector. We got lucky in those previous examples. In those previous examples, this expression happened to be something we'd seen before. That was weirdly fortunate. The only thing is, in this case, is that we simply haven't seen this expression before. It doesn't mean we can't compute it. And this is something, I'm not going to show you the computation, but it can be computed, and that's what it is. That integrand of this double integral is computed with this little formula. There's some details in here that are not conceptually that interesting. For the purposes of Math 212, I'm going to leave that out. But this is what the formula is. So putting that in to the integral, like so. This turns into that, and this is our first version of Green's theorem. It's kind of like a fundamental theorem of line integrals. It relates an evaluation over a region to an evaluation on its boundary, different kinds of evaluations. Nevertheless, very analogous. Let me pause here for questions. Does anyone have any questions about how this argument works? Yeah.
This is the R2 version exclusively?
Yeah, that's right. This is definitely just in R2 for a two-dimensional domain in R2. That's right, with a one-dimensional boundary curve. So let me encourage y'all to, I've thrown a lot of ideas at you all at once here, right? That's kind of the way this is. I think there's a lot of value in looking at this argument here, then look back at the fundamental theorem of calculus, the version that we gave of that sort of argument we gave motivating the fundamental theorem of calculus. And obviously they're not the same, but they're very analogous. And I think there's a lot of value in flip back and forth, look at those two pages, and persuade yourself that there are very analogous steps in this reasoning. And I think it makes this argument a little bit easier to swallow. Different ways to think about it. Okay, a little bit of notation. This little formula here, this thing that makes it all work that I didn't show you the details of the derivation of, I like to give this a name. I like to call it Green's operator because that's the operator that goes here. And I like to talk about it, and therefore I need a name for it, so I'm calling it Green's operator. The formula, Qx minus Py, you see that all over the place. Again, very standard We refer to the components of the vector field as P and Q. Okay. All right. So, yeah, punchline. Green's operator, that's the thing that is complementary to the boundary operation in the sense that if you take this vector field and over the boundary curve do that evaluation vector line integral, namely if you compute that, then that's the same as taking Green's operator on the original vector field and over the original two-dimensional region doing this kind of an evaluation, namely a double integral, giving you this, and the results are the same. So structurally, on this diagram, extremely analogous to the fundamental theorem of calculus, fundamental theorem of line integrals. Both of the fundamental theorems of line integrals. So this is arguably a fourth now version of that argument. Okay. All right. So here it is as a theorem. Be aware of the different notations. I like to refer to this as an integral of Green's operator. Most of the time you're going to see it written as integral dq dx minus dp dy, just more common notation. Okay. Right. So let's see an example of this. I'm going to entertain this question of computing a certain line integral. Here's the vector field we want to compute a line integral of. And the curve in question is the unit circle counterclockwise. Now again, you can view this as a Chapter 5 problem. We've got a vector field, we've got a curve, you can parameterize that curve, plug it into the usual formula, do the parameterization pullback, in other words. Gives you a single variable integral, and you can, again, take a deep breath and plow forward if you want. It's a lot of work, but you could do that. The alternative here is to realize that you have Green's theorem as an option. Just an option, may or may not be helpful. But let's see what that option is. Now, there's a requirement for this to work. Here we go. Notice, if you're interested in computing a line integral and you want to use Green's theorem, your domain has to be a boundary. It has to be a boundary of a two-dimensional region. And this is the catch for applying Green's theorem. Green's theorem helps you compute a line integral, but only if that curve is a boundary of a two-dimensional region. So we have to ask that question here: is this curve a boundary of a two-dimensional region? Whoops. Let's draw a picture of it. The curve is unit circle going counterclockwise. So is that curve a boundary of a two-dimensional region? Well, yeah, like just look at it and see, sure, exact, no problem. That is indeed the boundary of that two-dimensional region. So it is a boundary. Everybody on board? Now that's, again, as a student, as someone, taking a test, working a problem, this is your responsibility to notice this. Right? The question will not say, hint, notice this is a boundary, or use Green's theorem to compute, etc. The question very well might just say, hey, compute this line integral. And you can plow forward with Chapter 5 method, or you can notice that the curve happens to be a boundary, and therefore, once you realize that it's a boundary, then you can compute the line integral with Green's theorem. Namely, you compute the line integral by rewriting it as a double integral. And it's all over but details at this point. Green's operator, you've got to take your Q, take the x partial of it, You got to take your p, take the y partial of it. Conveniently, most of the ugly in that vector field disappears when you take those partials. Now, again, that won't always happen, but in this case, it really worked out nicely. And conveniently, Green's operator simplifies to just 2, which factors right out of the integral. You end up with just needing to compute the area of that domain. The area is pi. It's a unit disk. So, done. Really easy punchline.
Isn't this sort of strange? Because, like, so last section, we were also computing line integrals.
Yeah, that's a great question.
Now
Absolutely.
we're going in the opposite direction
Yeah.
to compute line integrals.
Well, that's right. Absolutely. These boundary theorems will go either way you like, right? So you can use Green's theorem. You can compute a line integral with a double integral like we did here, or you could compute a double integral with a line integral. We're actually going to do that in an example very shortly. The question is, which one happens to be more convenient for your purposes? And it just ends up, more often than not, it's more convenient as a tool for computing line integrals. So the analogy maybe kind of breaks down there, but it's an analogy of what's most convenient. It's not a mathematical. It doesn't break down the mathematical analogy. It breaks down the convenience analogy. Yeah, it's a great question. It's a good observation. Yeah.
So we can use this instead of what we've been doing?
Well, you know, if it works, right? But there's the catch, and you have to, this is always an issue. You've got to be sure that the curve over which you're computing a line integral is a boundary. And it's not a given. Not every curve is, right? Here's one. That curve, it's not the boundary of anything. So if this is the curve over which you want to compute a line integral, Green's theorem is useless. Does that make sense? Yeah. Sadly, all of these boundary theorems that we're going to talk about in this course they all have a little catch somewhere. You know, so the fundamental theorem of line integrals had a catch. The catch was, well, your vector field has to be a gradient of some function, and not everyone is. Sometimes they just aren't, and fundamental theorem of line integrals is useless. Yeah. Right. Okay. One more example. We're going to compute a line integral. We've got a vector field given. The curve is a weird curve. It goes along straight line segments between these various points. Here's a picture of it. The curve, so it starts here, it goes like that, and then down here, and then over there, and then back down to the origin. So it's kind of a rectangular, triangular figure 8, as it were. Nevertheless, that's a curve. You might want to compute a line integral over that curve. So the first thing to ask, and again, if we're going to use Green's theorem, our hope is that this is a boundary of something, and good news, it is. I'm going to break up that curve as a sum of two pieces of curve, and likewise the other one going this other way. And what we notice is that those three pieces of curve are exactly the boundary of D1, positively oriented D1. So, good news. Yay. Awkwardly, these other three pieces of curve are kind of going the wrong direction, right? And so they're going clockwise around D2. The good news is they're all going the wrong direction, and so in fact, the boundary of D2 is the exact negative of the sum of these three yellow curves. Said differently, these three yellow curves are the boundary of a negatively oriented D2. So it's a little bit of a weird case of curve being a boundary. This is a boundary of a sort of a strangely defined region. Nevertheless, this curve that we're given, that curve is a boundary. Seeing that it is a boundary, I can compute the line integral with a double integral using Green's theorem. This resulting double integral, of course, now again, there's sort of the positively oriented D1, there's the negatively oriented D2. That then I'm going to rewrite as two separate integrals, but they're two convenient separate integrals. Note that Green's operator ended up being just 1. So my integrand here is just 1. And those are two really easy integrals. Compute with geometry argument 0. Everybody good? Okay. I'm going to let y'all read this example here. It's a quickie. I think you can do that one on your own. It's very nice. I want to talk quickly about this other application. This is going to get to what you were asking about with the going the other way with it. I'm going to use Green's theorem here to compute a particular double integral. Specifically, I'm going to compute area. Kind of a cool little application. Area, of course, is typically computed as a double integral. It's a double integral of 1. And I claim that it's always computable by a line integral around its boundary. A particular line integral around its boundary. And the reason why is that if you look at that particular line integral, look at what you're computing a line integral of, interpret that appropriately as a line integral of a vector field. This vector field, when you compute Green's operator of it, you get 1. Now, it's an easy calculation. You know, dq dx minus dp dy. Q is x. So dq dx is 1. P is 0, so dp dy is 0. So Green's operator is 1. So this line integral is a double integral over d of 1, namely, it's the area. It's a really neat little trick. Now, one could argue that the, did we really make it easier? Area is something we computed long ago. It's just double integrals, no big deal. Now we've turned it into a vector line integral. So did we really help things? And it turns out that, yeah, in a lot of cases, this is really, really useful. And here's an instance that makes it really, really useful. If you are talking about a line segment, forget about the rest of this polygon for the moment. If you're looking at a single line segment, this integral is computed by 4-function arithmetic. Wonderful little fact. The magic line integral from the previous theorem. The average value of x over that interval times the change in y over that line segment. Now, I'm going to let you guys prove this theorem. It's not a hard proof. It's a very nice application. Just take an arbitrary line segment, starting point x1, y1, ending point x2, y2. Parameterize that straight line. That's a Chapter 2 problem. You guys should be able to parameterize that straight line. Compute this line integral directly from the definition. You're going to use your parameterization, plug in, take a couple derivatives, work it out, and you're going to get this as your result. It's a nice exercise. I encourage you to give that a shot. But the conclusion is really nice as well, and that is that you can compute that with 4-function arithmetic. So punchline, suppose you want to compute the area of a wacky polygon like this. Imagine how much of an inconvenience that would be using regular classical geometry. Weird angles, weird lengths, just no right angles in sight necessarily, and oh my gosh, what do you do? Right? And well, what you can do is just one at a time compute integral x dy with that handy little formula for each one of these pieces of curve and add them up. And so, for example, here is the polygon we were just looking at up there. The polygon had those 5 vertices, and that just gives you 5 faces and therefore 5 terms to compute, each of which is this 4-function arithmetic, which expanded out looks like that, and final answer. That's a lovely little application of Green's theorem. Okay, so I encourage you to check through the arithmetic here, and again, I think it would be a great exercise to prove this result. On a line segment, integral x dy is x bar delta y. Okay, so that's it for Green's theorem. I'm going to move on to Gauss's divergence theorem now. It's going to be the same thing again. Same basic idea. It's just that now we're going to, instead of looking at a 2-dimensional region in R2, we're going to look at a 3-dimensional region in R3. We're going to look at a solid like this, in other words. And we're going to try to relate a triple integral over a solid like that by taking its boundary and making analogous arguments to what we've done already. We're going to try to relate to, given a vector field, over that boundary surface, we're going to compute flux, and we're going to try to make that look like a triple integral. And again, good news, it's going to work out. But just a different sort of context for the same ideas. Okay. Now, we've gone through the following arguments several times, several different contexts. Single variable fundamental theorem of calculus. Arguably 2 different versions of the fundamental theorem of line integrals. Green's theorem. So we've got multiple versions under our belt. The big point, the thing that makes it all work out, is to realize that the thing that we're evaluating on the boundary accumulates, right? That all the stuff in the middle cancels, in other words. Different instances that shows up in different ways in the different instances we've looked at. So here, this is our picture. We've got a solid 3-dimensional region. And I'm going to consider what happens when I break that up into little pieces, little blocks, like that. There's going to be a bunch of little blocks. Right? And I want to know, is it true that the boundaries of all of these little blocks, when I add them all up, keeping in mind that boundaries are oriented, is it true that the sum of the boundaries of all these little blocks, is that equal, in fact, to just the boundary of the original thing? In other words, do all those interior faces disappear? Well, let's take a look at this picture. So here's a blown up view of 2 of these connected, sort of contiguous pieces. Let's look at this solid here, D1. That D1 has it has 6 different faces. I'm not going to draw all 6 of them, but it's got this face. It's got this face, and 4 more. Okay. Then there's this region over here. And it's got a bunch of faces. I'm going to draw a couple of these. It's got, well, let's see here. It's got that face. It's got a shared face. And then, sure, it's got this face and that face. A bunch of different faces. Okay. The one that's important is the one that's shared. This is the one I want to talk about for the moment. So that face, if I'm talking about boundary flux through this piece and boundary flux through that piece, that shared face is going to show up twice. Now, thought of as part of the boundary of D1, that face is oriented like that, outward, right? That's the rule. The orientation on a boundary face is oriented away from the solid that it's a boundary of. On the other hand, thought of as part of the boundary of this block over here, that face is oriented that way. Again, the rule is faces thought of as boundaries, pieces of boundaries of a solid, point away from the solid. All right, so that face then appears twice. This face appears twice in the summation. It appears oriented that way as part of the boundary of D2. It's oriented that way as part of the boundary of D1. Same face, opposite orientations, cancels. Everybody see how that works? So, look, it's geometrically different. It's when we were talking about Green's theorem, we had an edge with opposite orientations in the sense that it was two opposite directions along that shared curve. Here, the shared piece of boundary is a piece of surface. The two opposite orientations are opposite directions through the surface instead of along the curve. But it's still that it appears twice with opposite orientations and cancels. Geometrically different, but still very analogous. Right. Okay. So, punchline. The boundary of the entire solid is exactly equal to the sum of the boundaries of all the individual pieces. So this is where all the cancellation happens. Looking at the individual boundaries of the individual little pieces. There's all of these little shared faces in the inside. It's a network of lots of little shared faces. But each one of those interior faces appears twice with opposite signs, and so in the summation, cancels. And all that's left is the ones that aren't shared, namely the ones that are on the actual boundary of the actual solid. Okay. So that is what allows me to make this next argument here. Now, this page, try not to get overwhelmed with all the notation on the page. It looks a little scary, right? But this is an argument that y'all have seen 3 times already, just in a different form. I want you to, again, do a sort of a back and forth comparison. Look at the argument we're about to make here. Look at the argument we did for Green's theorem. Look at the analogous argument we did for the fundamental theorem of calculus. Same basic idea. So what we've just observed, this boundary evaluation accumulates over the interior pieces. So in this case, we're talking about flux through the boundary. And that is an accumulation of flux through the boundary of the individual pieces. That's the argument that we just made on the previous page. If something is true always, then it's true in the limit. Again, we did exactly that previously. Now look at this. That kind of smacks of a triple integral at this point. It's a summation, a limiting summation. It's a summation that's happening over an entire solid. Kind of really looks a lot like a triple integral. But triple integrals need to have volume there. So I'm going to multiply and divide by delta V. It's perfectly legal. I didn't do anything. They cancel. But now this looks like, it really looks like a triple integral at this point. Right? Limiting summation of something times delta V. All it remains to decide is what is this expression. It's sort of the limiting value of that expression. I'm skipping some rigor issues and formalities that aren't what I want the focus of this course to be. And again, bad news, just like with Green's theorem, this doesn't happen to be something that we've seen before. But the good news is, just like with Green's theorem, even though it's not previously familiar, it's still computable. And, there's a bunch of details that go into this that I'm not going to bother you all with. They don't go to intuition as I see it. And so I'm just going to tell you what the formula is, and here it is. So the integrand there is computed with that easy little formula. dp dx plus dq dy plus dr dz. Which is not hard, right? It's 3 partial derivatives. World's easiest derivatives. Okay. And so taking this and plugging it into there, this equation I can rewrite as that equation. And this is our first version of Gauss's divergence theorem. Now, before I go on, there's some notational little twists I want to put on this before I, really put a box around it. A better box, bigger box. But I want to, before I go on, notice that everything that we've done here, highly analogous to the Green's theorem calculation, is going to be a great exercise to, again, flip back and forth and persuade yourself that we're making morally the same argument. A couple of details different, appropriate to the different context, but morally practically the same. Okay. Now, this expression here, we're going to be able to talk later about the motivation for the following, but this has a name. It's called divergence. The divergence of our vector field. Thus, that notation. Very often it's just written as div f. Represent divergence. There is another way to write this that comes up a lot in physics classes. Now, those of you who are engineers, I don't know how much it's used, but in physics classes, the following notation I'm about to show you is extremely common. So here it is. It's a bit of a weird notation, but think back to gradients, right? Now, sort of a weird thing to bring up at this time, but gradient is defined by that formula. And if you look at this expression, there's something that's happening, 3 different things in 3 different components that are happening to the exact same function f. So that f, in some sense, in some sense, this is kind of what you're doing when you're taking the gradient, what you're doing to that function f. So, in fact, I get a little uncomfortable to write that, but I'm going to write that as itself a separate thing. That little symbol, what we've in the past called the gradient symbol, I'm going to view it as a vector of operators, right, of little differentiation operators. Now, once I've done that, notice that kind of shows up in this formula for divergence. Right? X partial, Y partial, Z partial. It's just that we're not doing, in this formula for divergence, we're not doing these 3 partials to the same single function like we did with gradients, but nevertheless there's an X partial, a Y partial, and a Z partial. In fact, it's the X partial, Y partial, Z partial of P, Q, and R. So I can kind of view that as a dot product. A little bit weird. X partial, Y partial, Z partial of P, Q, R. So that's my del operator dot what is in fact my original vector field. The vector field whose flux we're interested in here.
You call the upside triangle del?
Yeah, we call it the del operator. Sometimes depending on the context, you might call it the gradient operator, but here it's more commonly referred to as del. Yeah. So, kind of a weird notation, but it's actually really slick if you think about it. Del dot f. It's just really easy to write down on the page. It's kind of wonderfully coincidental seeming that it works out, that the notation makes so much sense, right? Very common notation. So you're going to see that all over the place. I like to use it a lot as well. So the punchline is that's how I'm going to very often represent it on the diagram. Remember, our whole goal here is we were taking boundaries of solids. We have now found the operator, the divergence operator, such that when you do flux of a vector field through that boundary, that you get as a result a triple integral of this divergence operator through the original solid. So, in the sense that these two resulting evaluations, these two resulting integrals end up being exactly equal, just like so many instances we've seen before, you can say that the divergence operator is sort of kind of complementary to the boundary operator. So again, just in terms of the way the diagram ends up looking, it smacks exactly like the fundamental theorem of calculus, fundamental theorem of line integrals, and Green's theorem. So, and now Gauss's divergence theorem. So let's see, I wrote this as a theorem here. And there it is. Everybody good? Yes?
Does this have, like, special circumstances where you can't use it?
Yeah, absolutely. Same deal, right? There's always a catch with all of our boundary theorems in this course. The catch here, you can kind of see the catch from the diagram. Let me do this, make the argument on the diagram. Suppose you want to compute a flux. Can you use Gauss's divergence theorem to compute just any flux? And we'll know that you can't. The catch is, and you'll note it, you see it right here, this only refers to fluxes through what are, in fact, boundaries. Right? And it goes into the very way that we derived this result was to start with a solid, and then let's look at its boundary. Right? So the result only applies if the flux you're interested in is a boundary. Again, you can always use these theorems in two different directions. So let's suppose this would be weird, but hypothetically, let's suppose you wanted to use this to compute a triple integral. This doesn't come up very often, by the way. Rare instances, you'll see one on the homework. But if you want to use it to compute a triple integral, note this is not just any triple integral. It's a triple integral critically of the divergence of some vector field. So if you're going to use it to compute a triple integral, your integrand, first, for one thing, has to actually be the divergence of some vector field. In other words, you're going to have to be able to, it's going to have to exist what you might call an anti-divergence. Turns out that for very large category functions, that actually is true. There is an anti-divergence. That's something that we're going to argue later on in this course. But the bigger worry is, can you actually find that anti-divergence? And that's a nastier problem, and it's something we're really basically not going to talk about in this course. Most of the time, we use the divergence theorem to compute flux by turning it into a triple integral. That's usually easier. Okay, let's get our hands dirty, do an example. We're going to compute the flux of that vector field through the unit sphere in R3 with a certain orientation. Now, just like with Green's theorem, just like with the fundamental theorem of line integrals, questions like this that are going to be highly susceptible to Gauss's divergence theorem will not really necessarily be announced as such, right? So notice in the statement of the question here, nowhere did it say, use Gauss's divergence theorem to compute such and such. It's phrased as a question which very well could be a Chapter 5 question. We know how to compute flux from Chapter 5. We've got this pullback formula, this capital N equals XU cross XV and all of that. Unit sphere, you can parameterize that. Spherical coordinates, no big deal. You can totally Chapter 5, plug and chug this question. So your job, one of your jobs as a student, is to be on the lookout for opportunities where a hopefully nicer solution might present itself. So you have to be the sort of the heads up on this. And if, in this case, you want to use the divergence theorem. Keep in mind we're trying to compute a flux, boundary flux. Well, we're trying to compute a flux. We have to worry about, is it true that the surface that I'm given, is it a boundary of some solid region? Right? Again, Gauss's divergence theorem, you can only use it, as I'm stating it here, if your surface is a boundary of some solid region. So that's not given in the statement of the question. You have to infer this from the question. You have to look at this surface that we're given, the unit sphere in R3. Let's draw a picture. Okay, the unit sphere in R3. Is that a boundary of some solid? And if so, what is the solid whose boundary is that unit sphere? Well, yeah, no problem. In this case, turns out, happily, it's the boundary of this ball, not this solid ball on the inside. Now, this will not always work out. Some surfaces simply are not boundaries. Here, for example, there is a surface. It's not a boundary of anything. This is the surface is intended to be. This surface, this piece of paper, it's not the boundary of anything. Right? So if you're interested in computing a flux through this non-boundary surface, Gauss's divergence theorem is not going to help you. Right? As I'm stating it here, there's a twist that comes later on. But in this case, lucky break, this surface is a boundary of that solid. So realizing that the surface is the boundary of a solid, I can rewrite the original flux integral over the surface as a triple integral over that solid. Everybody see how that worked? So that's where we use Gauss's divergence theorem. Again, it's on us to make the realization that it applies in this case. And so, again, I keep showing you these happy little examples where it works out super well. And in this case, look what happens to the vector field when you take the divergence of that vector field. Lots of stuff just disappears because of the way partial derivatives works, and that divergence ends up being 2, which factors out. You then just have to argue what is the volume of this unit ball, 4 pi over 3, and you're done. And we've computed that flux. Everybody see how that worked? Okay. This is actually a pretty good stopping point. The next discussion is going to take a while, so I'm going to let y'all out 30 seconds early. Okay. All right. See y'all later. See you next time.